Good morning, everybody. These brave people that be here in this morning after the barbecue. Okay, so, but we have a good reason to be here, not only to celebrate Marcelo Viana, but also because the quality of the talks. So I think that the title here is different. But
Changed a little bit, yes.
So it's a pleasure to me to announce the talk of Zoritch today. He's from Paris-Jussieu. He's going to talk about random square-tiled surface and random interval exchange permutations. Thank you.
So Rio is beautiful place. IMPA is beautiful place. So all the speakers had to give an excuse to be here, hoping to be invited again. I am not an exception. So I have to thank Marcelo for a certificate of mental sanity. I'm an intruder in the area. I came from differential topology, and at the beginning, experts took me for a crazy. I kept as a trophy a letter from Penn State, which is a reply to my application for sort of a postdoc position. And the letter said, to be considered for this position, an applicant is supposed to have research papers. What you are doing would not lead to a research paper. So we cannot consider you. So now I understand that people writing this letter actually had reasons, because I made some conjectures about interval exchange transformations, and for people from dynamics, there was not much difference at this time between interval exchange transformations of 2 intervals, 3 intervals, and 4 intervals. And also people knew that there is a theorem of Katok of never mixing and so on. So basically, at this time, many people sincerely thought that all interval exchange transformations are elliptic dynamical systems, like rotation of a circle. I came from topology, and for me, interval exchange transformations were surface foliations. And 2 and 3 intervals are foliations on the torus. And the torus is very different from surface of genus 2, 3, etc., because torus is the metric natural for the torus, it's flat metric, and for surfaces starting from genus 2, it's hyperbolic metric. So, and the certificate of sanity is, I was trying to advertise some conjectures, and everything somehow even were sort of explained in terms of some cocycle, and everything was nailed to Lyapunov exponents, but I had no technique how to work with Lyapunov exponents and how to prove anything about Lyapunov exponents. And thanks to first Giovanni Forni, who proved that at least they are non-trivial, and then to Artur and Marcelo, they proved that Lyapunov exponents, the spectrum of Lyapunov exponents is simple, and I had the certificate that, no, I am not crazy. So thanks a lot. And OK, now let me present several stories. So they would be sort of fragmented, and I hope to glue them together at the end of the day. And I will start with Mirzahari's count of simple closed geodesics. So when Vadim drew a closed geodesic, he made a picture of this style. Actually, curves on simple closed curves, the curves which do not have self-intersections on the surface, look rather like this. And only applying some smart diffeomorphism, you can unwrap them to, say, this way. So Mirzahari worked with simple closed curves, no self-intersections. And more generally, when you look at this picture, you do not know whether it's a single curve or whether there are several curves there. So it might be a multi-curve. And the way to work with multi-curves, how can one work with curves on the surface? One can consider homology. This is not good in this case because, for example, this cycle is non-existent for homology. Fundamental group is rather designed to work with self-intersecting curves. So here, the appropriate language is this space of measured laminations suggested by Thurston. And it somehow resembles homology. It has piecewise linear structure, but it doesn't have group structure. So I would hide most of the main part of this measured laminations under the carpet. So you have just to see that you can unwrap a curve like this to this much simpler way by applying a smart diffeomorphism. And now we can encode these components which are homotopic by a weight 3 here, 2 here, and we can associate also a reduced multi-curve to initial one. And now a fact from geometry. If you just draw your multi-curve on a surface, so I assume that there are no self-intersections and no intersection between components, you can, so this is a topological picture. Now I choose hyperbolic metric on the surface of genus 2, and I let my curves contract. They would contract to geodesics, and the fact is that the resulting geodesics would be simple. They wouldn't have self-intersections, and different components would not intersect between each other. And in this way, as soon as I introduce some hyperbolic metric, I can measure length of these curves. So I let them contract to geodesics. I measure the length of geodesics, and that's the length. And I can associate the total length to a multi-curve by recalling what were these weights of different components and computing the length of component weighted by these weights. So this is the length of a multi-curve like this. And now the counting problem. Denote by SXL gamma the number of simple closed geodesics, geodesic multi-curves on X, of topological type gamma. Topological type meaning that I can find some diffeomorphism of the surface which sends my multi-curve to this one. And so I measure the length in hyperbolic metric X, and I impose some bound L for the length. I say 1 million. And I count how many multi-curves of this topological type of length, at most 1 million in this particular hyperbolic metric, one can find. So I really insist that here we're counting simple closed curves and not all geodesics. If you take a random, well, not random, if you take sort of normal closed geodesic on a surface, it has tons of self-intersections. We're counting the peculiar ones which do not have self-intersections. They are rare, and they're more difficult to count. And here's a beautiful result of Mirzahani. So she proved that the asymptotics of this number of simple closed geodesic multi-curves of type gamma has the following form. So it is polynomial in the length, not exponential like all geodesics, polynomial. And the coefficient in this polynomial has this very fine structure. So there is part, this C of gamma, which depends only on topology. There is part which depends only on the metric and doesn't know anything about topological type of the multi-curve. And there is global coefficient which depends only on the genus and on the number of cusps. So, and actually, these C gammas are computable in terms of some intersection numbers. We'll come back to this later. So the corollary of this theorem is the following. Take two multi-curves of different topological types. For example, take just simple closed curves and take separating and non-separating. Then count how many separating simple closed geodesics in hyperbolic metric X of length at most L you can find, non-separating, and divide one over the another. So because of the structure of this coefficient, the result does not depend on hyperbolic metric. The hyperbolic metric disappeared in the answer. And this claim is that this ratio does not depend on hyperbolic metric. And I should say that when you see this theorem for the first time, it sounds completely crazy. How can it not depend on hyperbolic metric? I can create hyperbolic surfaces of arbitrary peculiar hyperbolic metric. I can pinch them. I can consider cyclic covers. Of course, they would have very particular length spectrum. So it is sort of the result on the opposite of what Vadim was telling. No, this thing does not see hyperbolic metric asymptotically. So if you just, I'm not speaking about the entire spectrum. I count them. and I consider only asymptotic number, and asymptotically, everything depends on topology of this multi-curve. Yes? Yes, of course. Numerator and denominator do depend. But when you take the ratio, asymptotically, the proportions depend only on topology of multi-curves. OK. Now, there were square-tiled surfaces in the title. I work with flat metrics. And with square-tiled surfaces, I'm completely obsessed by square-tiled surfaces. So maybe in some time, I will have to ask Marcelo for another certificate of sanity, because I was giving a talk at Harvard this summer, and there were presentations of speakers. And, well, this is Benson Farb, member of Academy of Arts and Sciences. This is Anton Zoritch, crazy person, obsessed by square-tiled surfaces. You can see, even at my look, that I'm obsessed with square-tiled surfaces. So I am. But they are really nice and really important. So square-tiled surfaces, what you see on the picture. So here, the square-tiled surface is a topological sphere. I just took 2 pieces of paper, of square-tiled paper, and glued them, put one atop the other, they're identical, and identified by the boundary. So topologically, when you identify 2 topological disks, you get a sphere. And we have a sphere, which is endowed with a flat metric, perfectly flat sphere, except that there are several points, this one, this one, this one, where metric has conical singularities. So here, metric does not have singularity, because when you identify 2 pieces of paper like this, you can unfold, and the gluing part disappeared. But you cannot flatten this corner, so they are conical singularities. I would distinguish the ones where there are only two adjacent squares, like this one or this one, where the conical angle is pi. So, and I forget other points. And, well, my square-tiled surface is filled with horizontal circles. And I shaded in different colors the maximal cylinders. So here you have, so these 2, well, these squares, they correspond to 1 cylinder, where all horizontal curves are like this. This is another cylinder. Here we have a long cylinder, and one more here. So I will associate to any square-tiled surface the following multi-curve. I will take the central horizontal curves of these maximal cylinders, these red ones, and also I will mark all the points where we have cone angle pi. And traditionally, say, when you have a complex curve with marked points, hyperbolic geometers say, let's consider cusps at these points, cusps of hyperbolic metric. So that's what I do. So to every square-tiled surface, you can associate the topological surface with a certain number of cusps and the multi-curve on it. And also, when you have a picture like this, I can construct many square-tiled surfaces of this type. And I consider, say, all of them tiled with at most 1,000,000 squares. And now the theorem. For any topological class of a multi-curve, the frequency, which we have just seen, the C of gamma in the theorem of Mirzakhani of corresponding hyperbolic multi-geodesics, is the same as frequency of square-tiled surfaces of the corresponding type. So there is a bridge between hyperbolic and flat geometry in terms of sort of simple closed geodesics. So here you can consider this picture on the right as flat multi-geodesic, where we have family of flat geodesics, horizontal geodesics here, 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 here. And the claim is that frequencies are the same. OK. Now I would like to use it. And I would like to discuss a bit in more details the shapes of random multi-curves and random square-tiled surfaces on surface of genus 2. So when we have a multi-curve like this, we have seen that they have certain frequencies. One can compare these frequencies and ask which behavior is more frequent and which behavior is less frequent. For example, which simple closed geodesics are more frequent, separating or non-separating? Or you can ask, you take a random primitive multi-curve like this of length at most milliard, and you compare frequencies with which certain event happened. For example, you can ask how often the associated reduced multi-curve separates the surface, or how often it has 1, 2, 3 primitive components, and all these kind of questions. So here is the answer. So you can, what was hidden in my statement of theorem of Mirzakhani is that you can compute these frequencies. They're really efficiently computable for loud genera. And in genus 2, when there are no cusps, there are only 6 topological types of primitive multicurves, and the frequencies of corresponding types are presented here on the slide. For example, comparing these two numbers, you see that non-separating simple closed geodesics are much more frequent than separating ones. And it becomes even more drastic for larger genera. I should say that I'm fascinated by the fact that Mariam has computed many frequencies like this just without debugging and without comparison with some databases absolutely correctly. But here, unfortunately, there is a misprint in her paper, which was reproduced many times. So in many, many lectures, the answer is 1/6. No, the ratio is 1/48. So when we ran in this mismatch, we were frightened to death, but then it was verified by many ways, and we're debugging our results and trying to compare it with other ones and compute experiments anyway. By now, it is confirmed. So, OK, so actually, this table gives you the answers to all questions which I asked, except that there is a trouble. When we pass to genus 3, the table contains already 41 pictures, and when we pass to genus 5, there is this 4,500 pictures, and what do you do with all this data? So you want to know sort of quantitative answers to your questions. What is more common? What is, and you have just a table of 4.5 types of pictures with all these numbers. What do you do with them? So the natural question is to try to somehow analyze it and to try to find out what pictures are really carry most of the frequency and which appear particularly rarely. So to specify what do I mean by random multi-curve, let me give 2 examples of analogous structures. So when we have any structure which can be decomposable into sort of elementary blocks, they're often theorems of asymptotic description of this block decomposition. So here's the first example. Consider random integers in the following sense. You take very large segment from 1 to n, where n capital is really huge, or from n to 2n, where this capital N is really huge. And you make statistics of how integers in this segment decompose into, well, on prime decomposition. So in this particular example, I'm not interested by these powers. I'm only interested by the number of elements in my prime decomposition. Prime number theorem tells how often, asymptotically, when n is huge, you see a prime just on the nose. And this Erdős-Katz theorem says, what should you expect from this decomposition? How many elements are the most common? And that's the answer. So actually, the result is very precise and, to my mind, extremely beautiful. And here's another example. So let's consider permutations. And in this setting, I will consider uniformly random permutations. So we fix number n of elements. We consider n factorial permutations. We assume that they're equidistributed, equiprobable. We take by chance, well, we take a permutation. And the question is, what can one say about decomposition of this random permutation in the product of cycles. So it was, so here one can really write the answer in terms of these unsigned Stirling numbers of the first kind, and when n is large, one can give very well described statistics of this number of cycles in the random permutation of n elements. So there are not so many cycles, approximately log n. So this is their mean value. This is variance, and actually this is their central limits theorem for statistics of cyclic decomposition of random permutation. I would like to do more or less the same thing. So I'm taking, for example, I fix the genus and number of cusps, and I consider square tile surfaces tiled with at most million squares, and I collect statistics how often I see square tile surfaces with one horizontal cylinder, two horizontal cylinders, and so on. Then I let my million tend to infinity, and I consider limiting statistics. And now, when I already computed my limiting statistics, I'm studying what happens with the statistics when genus grows. So they're sort of, I'm passing to two limits. First, I fix the genus, I let the number of squares tend to infinity, or I fix the genus and I consider longer and longer multi-curves, and I collect statistics on frequency of multi-curves, and then I look what happens when genus is large. So, and I repeat all the equations which were already on the blackboard. And note that this theorem, which relates frequencies of hyperbolic multi-geodesics and square tile surfaces, tells that actually we are working in parallel with two identical statistics, because there is this language of passing through frequency of hyperbolic multi-geodesics to frequency of square tile surfaces. Okay, so now I can give you the answers. So first, if you take a random multi-curve, then the associated reduced multi-curve has one of these shapes with probability which tends to 1 when genus tends to infinity. So one of these shapes meaning the following. First, there are not so many components, approximately log g over 2. So we've already heard here that log is not a function, it's a constant, and not such a large constant. So you have I don't know whether anybody had experience of working with surfaces of genus larger than 10,000. For me, it was the maximum. We made the experiments with surfaces of genus 10,000, but for 10,000, log g over 2, it's nothing. So they're just like 6, 7, or 8 components with very high probability. And this can be specified. And in terms of square tile surfaces, it means that you have just several cylinders. In principle, you can have from 1 to 3g minus 3 maximal cylinders. I consider I'm simplifying the story. I assume that there are no cusps anymore to get rid of one of parameters, just to work with genus. So there are no corners of angle pi. And most of square tile surfaces, they have just several maximal cylinders. And what is even more interesting, look, so if I chop my surface by all these components, I do not disconnect it. In terms of square tile surfaces, it means that all, yeah, oh, I hope I have a, no, I don't have this slide. It means that all conical singularities of a random square tile surface of large genus, they sit on the same horizontal leaf and on the same vertical leaf. So for me, as for differential topologists by education, this is sort of completely counterintuitive, because I started my education from Morse theory, and in Morse theory, you take Morse function, all the critical points are at different levels. Here, there are plenty of them, and they all sit at the same level horizontally and the same level vertically with probability which tends to 1 when genus tends to infinity. So this is one thing. Another, now I have to come back to random permutations. Namely, I will introduce a strange probability measure on the set of permutations. I will consider permutation not equidistributed, but I will twist a bit the measure. And if somebody has seen Evans' measure, this is very similar to Evans' 1/2 measure. So I will do the following thing. If the cycle type of a permutation is, well, mu1 cycles of length 1, mu2 cycles of length 2, etc. So if the cyclic type is like this, I associate to my permutation this number. So I take certain number, certain parameter, which I fix once and forever, theta1 power mu1, theta2 power mu2, etc. So the parameters are like this. It's zeta of 2g divided by 2. So if there would be no zeta but just 1, if all parameters would be 1/2, this would be called Evans' measure, and it somehow this number becomes small when there are many cycles, and it is larger when there are few cycles, when there are not so many cycles. And so this is a way to somehow give certain favor to permutations which do not have too many cycles. Actually, this parameter, when g is sufficiently large, zeta of 2g becomes very close to 1. So for g starting from, I don't know, 10, this is almost 1/2. And now I sum up all these weights, I normalize them by them, and I get probability measure. And I take my permutations with this strange measure, which somehow more favorable to permutations which don't have many cycles. And here, so actually people in combinatorics relatively recently, around 94, 95, they made enormous advance in the study of random permutations, and I would say that basically everything is known, and there is a technique which is called mode-Poisson convergence, which describes the statistics of corresponding random permutations perfectly well. So the theorem which we proved is that morally the statistics of this hyperbolic, simple closed hyperbolic geodesics or square-tiled surfaces becomes basically undistinguishable from statistics of these random permutations with this strange random measure which I described. So this is, I do not go into details on basically indistinguishable. This is very well formalized in terms of this mode-Poisson convergence, and this is extremely good convergence, sort of in some sense, say it's so there is convergence of all uniform convergence of all moments of two distributions and so on. So we can tell plenty of things. We have large information about large deviation. I don't want to bother you with all the details, but just believe me that the information is really very precise. Now, what I have to say, at least one word of what is hidden. How was the proof obtained? So the frequencies I was speaking about, these rational numbers which appeared at some point on the blackboard, they're calculated using these intersection numbers. So you have to take the moduli space MGN, take the Lin-Mumford simplification. So this is Riemann surface of genus G with n mark points. You can consider every mark point a cotangent, since it's complex curve, cotangent line. So we get, when we vary surface and mark point, we get a line bundle over MGN bar. It is known that this line bundle is holomorphic line bundle. It has first Chern class. It is denoted by Psi1 for the first mark point, Psi2 by the second mark point, and so on. And if you multiply these guys with powers d1, etc., dn in such a way that sum of these powers becomes dimension of the moduli space, then you can integrate this cohomology class over the base, and you get what algebraic geometers call intersection number, and physicists call it Witten-Kontsevich correlator. And this is extremely famous guy, and there were sort of 4 Fields medals designated for different proofs and different things about Witten conjecture, telling that these numbers, if you wrap them to some generating function, then this generating function is very special and satisfies certain equations. So one of the way to reformulate this Witten's conjecture is to say that these numbers, which are rational numbers because this is an orbifold and not quite a complex manifold, so it's these positive rational numbers, they satisfy certain recursion, which is called Virasoro constraints, and this recursion is complicated. It is really complicated. It is sort of easy to write down, but when you program this recursion and you try to compute these numbers on a computer, you go to, say, genus 6 and n equal to 10, and your computer says, no, I cannot do it. So there are plenty of things proved by these numbers, but basically up to recently it was very difficult to work with them. And this theorem of Amol-Agarwal tells that all these numbers, numerically, they can be represented by this, well, basically expression in factorials with an error term which is uniformly small for all partitions D1, etc., Dn, as soon as n is not too large compared to G. So this is, for me, the best comparison is Stirling formula. So we know, so for n factorial, we have a very simple recursive formula. What can be simpler? We know values of n factorial, say everybody knows up to 5 factorial. Some people remember 6 factorial and 7 factorial. But when you work with really n factorial, you use Stirling formula. You do not use factorial. So this is sort of Stirling formula for intersection numbers. And to my mind, the beauty of this formula is that, well, first, it is simple. And second, it's uniformly good approximation for tons of partitions. And actually, the proof is also beautiful because the proof is based on some very deterministic recursion. And what this guy uses, he uses a biased random walk. There are several terms in this recursion, and one term asymptotically appears with sort of probability 1/3, and the other term with probability 2/3. And the nasty term, which makes partition longer, appears with probability 1/3, but the nice term, which we like, which shortens the partition, appears with probability 2/3. And he proves that this contraction somehow is dominating, and then, yeah, and this is, the proof is not that complicated, and to my mind, really beautiful and unexpected. Now, one more word. So I was speaking, I did not specify it, but when I was speaking about random square-tiled surfaces, actually I considered square-tiled surfaces which correspond to quadratic differentials. One can consider more restricted square-tiled surfaces where you not only have vertical direction and horizontal direction, but when you have sort of oriented vertical direction, when you always know direction to the north and when you always know what is the direction to the east. And you can compute square-tiled surfaces like this. Conjecturally, statistics of cylinder decomposition and such is just very well approximated by statistics of random permutations, where this time I do not need to take crazy measure, just uniformly random permutations. And this is probably the first time in my experience when abelian differentials are combinatorially more complicated than quadratic differentials. Up to now, it was always other way. And here, we first had this conjecture. We still have no idea how to prove it. we managed to prove conjecture for quadratic ones, and for abelians, up to now, we do not have serious clue how to advance it. And yeah, probably, yeah, I'll come to this. And now I still have some time, which is excellent. I will show how all this can be applied to seemingly extremely naive problem. And the problem is Arnold's problem formulated in 2002. So there is a whole book, Arnold's Problems, and this book appeared like this. So Arnold had a famous seminar in Moscow, and every year, the first seminar, it was difficult to enter the room because it was known that at the first seminar, Arnold announces a list of about 15 problems, which are, most of them were interesting. And everybody wanted, what can be more precious than interesting problem, right? So, and he collected them, and at some point, he just published all the problems of Arnold's seminar starting from 57 or 59. So this is a problem of 2002, and you see it's on the blackboard. So he defines a CBA permutation as follows. You take all integers from 1 to n, and then you chop this segment of integers into 3 parts. The part at the beginning from 1 to a, then from a plus 1 to a plus b, and then from a plus b plus 1 to the end. And then you permute these pieces like CBA. So basically, you recognize interval exchange transformation of type 3 to 1 with integer length of subintervals. Except that he considers this interval exchange transformation as a permutation, why not? And he asks, how often do you see this or that cyclic decomposition in permutations like this when this number n becomes really very large? So you take by random this interval exchange permutation by random in a very long, well, assuming this n is very long, and you take this a's and b's by random, and you ask, what is the cyclic decomposition of this permutation? So you see this problem is sort of in the spirit of what we just considered. Let me illustrate what he calls, so he says, so this is I took the statement of the problem literally from the book. So he distinguishes permutations which permute cyclically, and he says like addition of a constant to the, well, mod n, or transitively, like addition of the constant 1. So let me give 2 examples. So here's just an interval exchange permutation of 11 elements. I chop here and chop here. And to make picture somehow easier, I colored them in three colors. So you take this red interval of length 2, you put it at the end, this green interval at the beginning, and blue interval is moved a little bit to the right, and it's in the middle. And let's consider the cyclic decomposition of this permutation. To consider cyclic decomposition, it's easy to consider a suspension over interval exchange transformation. So I consider a polygon like this. I identify this side with this side by parallel translation, this side with this side, and I consider vertical flow. So it's really suspension over interval exchange transformation. And if we want to find the orbit of, for example, element 1, well, I move up here to this part of the red segment. I jump here instantly. I continue up. The next element is 10. Then I continue from 10 up. I jump here. I get to 4. And in this way, we get a cycle. Oops. We get a cycle 1, 10, 4, 7, and 7 when we go up. We get here. We come back to 1, so it's really closed up. And I can make a similar drawing for other elements. We see that we have 3 cycles. So this permutation is neither cyclic nor transitive. We have cycles of different length. OK, I change parameters. And for when the segment A is of length 2, segment B of length 4, and segment C of length 4, I have this decomposition into cycles. So for Arnold, this is a cyclic but non-transitive permutation. So if you take these 2 cycles and, for example, consider them as an ordered set, you it's the same as this decomposition, and this really mimics a cyclic permutation. And finally, this is an example. I change the length parameters one more time, and we get a single cycle like this. For Arnold, this is a transitive permutation. You visit all the elements, so we really get a long, as a cyclic decomposition of permutation, we get a long cycle. OK, so let us look a bit more attentively on the suspension flow on the corresponding surface. And for this, let me rearrange a little bit the polygon. So I take my scissors, I cut out this triangle, and since this green side is glued to this green side, I can put this triangle and reglue it here. And then I take scissors again, and I put this triangle here. And now you recognize what surface do we have. We're on a torus. And what we consider is the first return map from this transversal to the vertical flow. And we're interested in properties of this first return map. So let me go even further. Let me rearrange the torus a bit more. So I assume that I considered vectors of my suspension as integer vectors. So they live on an integer lattice. So my torus is square-tiled. I have a square-tiled torus. And I can represent it as just a vertical cylinder with some identification of two sides. And this identification is a twist. So for the first example, we have this picture. And now it is particularly easy to see why the corresponding permutation is neither transitive nor cyclic, because this is the endpoint of our segment. And the structure of this yellow and purple trajectories is really different from the structure of this green trajectory. Now, oops, sorry, I manipulate badly the remote control. So in the second example, it is already better. The torus is like this. And the endpoints of the interval are both on this boundary circle. So basically, they're on the same vertical leaf of our flow. And finally, this one, not only both endpoints on the same vertical leaf of the flow, but we have just one vertical band of squares, and this is an example of transitive permutation. OK, so this is a sort of geometric interpretation. Let me consider one more counting problem. I already confessed that I'm obsessed with square-tiled surfaces. I like to count them. Let me count two kinds of square-tiled surfaces, two square-tiled tori. So I can count square-tiled tori with two mark points. One point, you mark sort of, you always mark a point on the torus, but here we have this blue point and red point. And first, I consider generic situation when this blue point and red points, well, I assume that they're in the vertices of my square tiling. So I consider generic situation when they do not belong to the same vertical leaf. Well, there are several parameters, and it's not so difficult to make a count. I count square-tiled tori like this, tiled with at most n squares. And I count asymptotics. So we have this perimeter of the cylinder. We have height of this, well, this distance between boundary components. We have integer twist, which we use to glue boundary components. And this integer twist varies from 0 to w, because when it's more than w, I can apply then twist and untwist it to have this twist parameter between 0 and w. And, well, I also have to record position of this red point. Since time is going fast, I just suggest to look at the answer. The asymptotics is approximately, well, the n cubed over 3 times p squared over 6. Excellent. Now let me count other square-tiled tori. This time I count ones where the red point and blue point are on the same vertical leaf. And I also fix this distance h. So I consider much more restrictive count. I imposed the given distance h, and I impose to the red and to blue points to be on the same vertical leaf. I make a count, and surprise, it's still n cubed. But coefficient is different. But one can just follow the calculation. It's elementary, and surprisingly, it's still n cubed, meaning that the frequency of these guys is sort of the same order and the frequency of the previous ones. And in particular, I can compute frequency of those which have a single band of squares, so the ones for which h is equal to 1, among all of them, and the answer is 6 over pi squared. And here's a theorem of Pak and Redlich of 2008, where they compute frequency of this transitive versa cyclic ABC permutations, and what the coincidence, the number is the same. So you can guess now what would be the theorem. That the theorem is that it is not a coincidence, that these two numbers are really the same. And this is a sort of a solution to Arnold's problem. So if you have some interval exchange permutation, so we have, for example, corresponding to this more complicated permutation for 3 to 1. This is the permutation which one uses speaking about interval exchange transformations. Usually permutation for 3 to 1. OK, so then we fix this permutation. We consider length of subintervals. Here we have these guys. So we can repeat everything which I told about the torus. And we construct suspension. We get to some stratum of abelian differentials. And the claim is that the frequency of permutations of these interval exchange permutations with plenty of elements and fixed combinatorics is the same as the ratio of of count of square tiled surfaces in the resulting stratum of abelian differentials with k cylinders over all square tiled surfaces. And actually, we could even enhance a little bit this theorem. Namely, you can do the following. You can start with a true interval exchange transformation with irrational length. And then you consider, so there are n parameters, the length of subintervals. We fix combinatorics, and we just consider we vary a little bit the length. And I consider a small ball in Rn varying this length. And in this small ball, I consider a net where all the lengths are proportional. So, and I make my statistics only in this small ball, and I make my net smaller and smaller, finer and finer. So I consider sort of rational interval exchange transformations inside a ball of parameters. And the frequency does not depend on the ball. It's everywhere the same. And actually, here I forgot to say, it's a conference on dynamical systems. I'm speaking about combinatorics all the time. The result of Mirzahani on her frequencies result is strongly based on ergodicity of the mapping class group. So dynamics is there. Nothing would be there without this theorem from dynamics. Here, I'm also using dynamics. I'm using actually ergodicity of Teichmüller geodesic flow and of GL2 action. So dynamics is a little bit hidden, but basically it's the ground of everything. OK. Now, to show off, I can suggest answers in some low-dimensional strata. And this is this is for 4 elements. This is the stratum, the other permutations. The answers become more complicated. Oops. And if you go to the next stratum, the answers become even more complicated. And this is mostly to scare you. And what I'm saying is that the story now resembles what I was presenting before, that you have these long tables of answers, and what do you do with them? And you consider large genus asymptotics. And unfortunately, as I said, we don't have the complete description of of random square tile surfaces, which are a billion, but at least we have analog of prime number theorem. We know, due to results of colleagues, we know asymptotics for volume, Mazorovich volume, which is sort of count of all square tile surfaces. We found their contribution to this volume of one cylinder square tile surfaces, and both expressions are fairly nice. You take the ratio, and you see that when permutation which you use is long enough, then their proportion of transitive and cyclic permutations compared to all permutations is approximately, is very well approximated by 1 over number of elements in our permutation. So this is a rigorous result, and unfortunately, the most general question of Arnold, what is the statistics of Young diagrams of this all cyclic decomposition, is conjecturally just the same as statistics of permutations, but it's a conjecture. Now, just 2 last words. I started at 2. I am already like over time for 1 minute, but just 2 last words. I would like to defend the word conjecture, and I insist that, to my mind, one should make a distinction between a conjecture and a guess. So, Stas at his lecture said, he was speaking about Mandelbrot. He said that he made tons of conjectures and 10% of them were correct, and here it's, no, it's not a conjecture. This is a guess. The conjecture is when you elaborate some, for example, smart computer experiment, and then you make this computer experiment. So here, when I am saying conjecture, it is approximately 2 years of CPU time of turning of my computer, and experiments with different strata and different surfaces. So we worked with dimensions between 400 and 20,000. So I really, when I said that we went to genus 10,000, it was serious. We played with interval exchange transformations of 20,000 subintervals and collected the statistics. And so here is the statistical analysis. So the conclusion of all this is the following, and it's more or less all the philosophy of this story. You try to understand the structure of some objects like square tile surfaces, multi-geodesics. You get nice formulas. You can apply them to small genera, but starting from some point, the tables become unbearable. But fortunately, in many, many situations, when you go to higher genus, despite the fact that the true life, the exact life, becomes unbearably complicated, asymptotically, the asymptotic answers are extremely simple and beautiful. So this is propaganda for asymptotic answers. And thank you very much, and happy birthday, Marcelo.
So are there any comments, questions?
At some point, you mentioned intersection number and Witten-Kontsevich correlations, and said that there is some physics hidden there. Well, as far as I understand. Can you comment?
Yeah. So I can. Okay, I'm almost there. Yes, it's here. So I was thinking about this object, and this equality is just notational equality. Algebraic geometries denote this number like this, and for them, this is intersection number. And it's a sort of definition of intersection number. You have some cohomology classes, you integrate them over a manifold, well, in this case, orbifold, you get what algebraic geometries called intersection number. So on the right, this is the notations which use mathematical physicists for the very same object. And so this is it's just notational equality, and guys are called Witten-Kontsevich correlators. And well, for physicists, I do not dare to comment about the origin where they appear in physics, but by some physical motivations, Witten conjectured that their generating function for these numbers, so when you have, you see here you have tons of numbers which are, well, specified by partitions of 3g minus 3 plus n. When you have tons of numbers like this, the best way to treat them is to wrap them in one generating function, adding some formal parameters, and then considering corresponding series. So he conjectured that the corresponding generating function satisfies certain equations. And at this time, it was completely unexpected. And this is Witten's conjecture. And it was proved, the first proof was by Kontsevich. Then there were proofs by Akunkov Pandaripande, by Maria Mirzahani, by Landau and Kazaryan, by other people. So there, I think that nowadays there are about 10 different proofs, really different proofs. And so when you say that your generating function satisfies some differential equation, combinatorially, it is basically, usually it's basically the same as to say that ingredients satisfy certain recurrence relations. So it is known that these recurrence relations are called Virasoro constraints, and it is known that all these numbers are uniquely defined by two starting numbers and by these recurrence relations. And so this is briefly this story. And these guys, they appear in really various problems of geometry, combinatorics, sort of they pop up everywhere. They are really, really important.
Any other questions or comments? So let's thanks again.
That's me who thank the audience for courageously coming to the first talk after conference dinner. It's heroic.